which we have started like 5 or 6 months before, and it's kind of a series. We are inviting very renowned academic um, scientists throughout the India and from abroad, and who have shared their thoughts and their work in this lecture series. And in this scenario, so today we have Professor Manas K. Ghorai from IIT Kanpur, and I will request Dr. Venkatesh to introduce our lecture for today.
Thank you, Dr. Deepak, for briefly explaining about Acharya Prafulla Chandra Ray's lecture series we are conducting at IIT Indore Department of Chemistry. So today we have a renowned speaker, Professor Manas Ghorai from Department of Chemistry at IIT Kanpur. Today he will speak about domino ring opening reaction and ring opening reactions of small heterocycles. Before he begins his talk, briefly I would explain about his accomplishments and his journey in research career. Professor Manas Ghorai, born in West Bengal, did his master's from Indian Institute of Technology, Kharagpur in 1991. So after finishing his master's from IIT, he joined with Professor Ganesh Pandey at National Chemical Laboratory to do his PhD in synthetic organic chemistry, completed PhD in 1998. So after completing PhD from very reputed institute, he did his postdoctoral research with Professor Michael Schmittel at the University of Würzburg, Germany for 2 years, following by which he was awarded one of the most prestigious fellowships in the world, Alexander von Humboldt Fellowships. And he worked at the University of Siegen for 2 years. After this, he moved to United States of America, MIT, to do another postdoctoral stint with Professor John Strebe in synthetic organic chemistry, following which he was awarded assistant professor position at Indian Institute of Technology, Kanpur, in Department of Chemistry in 2002. So soon he was promoted and he became a full professor by 2012, and he is also a USV chair professor. He is a fellow of many Academy of Sciences, for example, National Academy of Sciences, Allahabad, West Bengal Academy of Science and Technology. He is also a fellow of the Academy of Sciences, Bangalore. His research interests mainly revolve around synthetic and mechanistic investigation of small molecule heterocycles like acidins using organocatalysis and dianion chemistry, and also using chiral catalysis. So with this brief introduction about him, I would welcome Professor Manas Ghorai to begin his talk for today.
Good afternoon. First of all, I thank the organizing committee, Dr. Deepak and Dr. Venkatesh, for giving me this opportunity to present some of our work in this Acharya Prafulla Chandra Ray lecture series. It's my honor and privilege. So, Venkatesh is our student, and I was sitting in the table is Madam Ila's table. I still keep that table and some of her chairs. I still continue that office. And I've been here almost 20 years. And so my research group involved in asymmetric synthesis based on S-type ring opening of small ring heterocycles, memory of chirality, that memory of chirality concept. We are the only group in the country still today we practice. Organocatalysis, many people does that. Enolate anion and dianion chemistry. And I'll be talking today this SN2-type ring opening of small ring heterocycles. As the title says, rock and rock of small ring heterocycle chemistry. Rock, as Dr. Venkatesh told, domino ring opening cycles is the terminology given by us to the scientific community, and ring opening cycles is rock. So for the benefit of the students and some of the faculties who is not aware of our research, I'll give the origin of the problem. I started and still continuing for almost last 19 years. And today's date, lot of advanced chemistry. I'm not pointing out or criticizing that. All material chemistry, metal mediated chemistry, I mean, huge. But I stick to that most, in this, basic domain. So agitated chemistry, as my title says, the types of agitatins and agitatins and their mode of activation. So ring opening chemistry of N-sulfonyl agitatins and agitatins is interesting for synthetic purpose due to selective CN bond cleavage, useful in the synthesis of important nitrogenous compounds, stable, generally solid, and easy to prepare in large scale, industrially important. That's why N-sulfonyl. And types of agitatins, their mode of activation, intermediate, hit upon the nucleophilic activation, that I'll be telling before I go to the next one. So agitatins or agitatins will be activated if there are electron-withering groups like COR, CO2ET, sulfonyl, etc. are attached to the nitrogen, this one. So this one, electron-withering group. So if there are electron-withering groups, there are no further activation needed. If the strong nucleophile, it will undergo nucleophilic ring opening reaction. If not, then there is a Lewis acid coordination. It's from this agitatinium ion and followed by this CN cleavage. In both the cases, CN cleavage, you get this product. If there could be activated another kind, where this called R2 is maybe some donor group and electron-withering group. So donor acceptor type of agitatins, and there also again protecting groups are there. And in this case, you put Lewis acid, there is a directed CC bond cleavage. And I'm not discussing about the non-activated, because if there are alkyl, aryl, all other groups are there, that's called non-activated, and in those cases, activation is required, like either protonation or quaternization is needed. I'm not discussing that. So reaction of agitatins and agitatins. So agitatins and agitatins can undergo ring opening reactions, cycloaddition and ring expansion reactions, rearrangement and fragmentation reactions. So what is known in agitatin and agitatin chemistry? So before we enter in the field, so Lewis acid activated ring opening of 2-aryl N-tosyl agitatins and agitatins, earlier proposed mechanism what? So if you start with the enantiopure agitatins or agitatins, with Lewis acid, in presence of Lewis acid, it undergoes this CN1 cleavage, formation of this benzylic cation and N- sulfonyl. So people used to think that because of this benzyl cation is stabilized and this is stabilized, is from a stable dipole. Obviously, if you do the nucleophilic ring opening reactions, one could expect that there is a product is racemic. Similarly, there are many other, whether it's alkyl, alkynyl, silyl methyl, and all the cases people found out that this reaction is going through SN1 pathway, giving racemic products starting from enantiomer compound. And this is known from 1970s, and that Yama or many other groups, they started this reaction. And the origin of the problem. When I joined in IIT Kanpur in 2002, my first research proposal was memory of kinetics. That means if you see an amino acid like this, for example, phenylalanine, and it's N-Boc benzyl, and if you put a enolate, so then basically one should expect that it's sp2 planar, and once you alkylate, you get the racemic product. But our concept, not my original, is not mine, but I have utilized the concept. It was known from Kawat and Fuji from Japan from 90s. In that case, because of these two different protecting with the nitrogen, there is a axial current in the enolate. Then one can have a non-racemic product based on the part of the intermediate you can freeze. So based on this, these are my first proposal, and I was only one or two students. Initially, one student and then two students started the reaction. We thought, then the student is complaining that nothing is moving, nothing is going. So we thought, you take this amino acid, enolate, and take one imine, so that alpha beta diamino ester derivatives you can get, and based on the report, we got it in 2001, and I joined in 2002, that they have used this, chiral amide enolate, and they took this aziridine as a electrophile. So obviously this enolate, and as you know, the SN2 reaction, it should attack from the less substituted sites here or here, and you get this, this product. And once you get this product, then finally you can cyclize. And based on, because of this, there is a aziridines are enantiomer, so you should have two chiral center. So from the diastolic excess of the NMR, you can find out that what are the induction in your first CC bond reaction step. So based on this idea, we thought, okay, since we are not getting any product or any information, we are getting product but unable to find out that what is going on. All NMRs like wave. So we thought maybe again our lab was surrounded by all inorganic chemists. So you take this. I told my first student that take aziridine, you make it the aziridine, and take maybe zinc bromide. So zinc bromide will activate aziridine, and this enolate will open, and you get this product will get. And from the NMR, we'll find out that what is the diastolic excess of the product, and accordingly we can correlate what is the enantiomeric excess. But initially, to our great surprise, we didn't get this product. It was the enolate was basically dummy. But we got some product. In the simple product, it was difficult for me to analyze because our attention was towards this your ring opening product. But then it turned out to be this product is actually this zinc bromide we use as a Lewis acid. It was opening by the bromide anion. And then I asked my student, just for curiosity, just take the rotation. And he reported me, said this was showing optical activity. I was, what rubbish? How it can be active activity? It is known in the literature that Lewis acid catalyzed ring opening reactions of aziridine, do proceed through an 1,3 or 1,4 dipolar intermediate. So this is basically the beginning of a new era, and obviously, and it created a lot of controversy and repercussion across the world, India and abroad. What is going on? Because all big, I will not tell anybody's name, India or abroad. Many big people are involved in this aziridine and aziridine chemistry. People have used it in India also. Many people have used as a electrophile or as a building block, some with the other. So what is known in the literature that this Lewis acid catalyzed ring opening reaction, it should proceed through this. But based on our optical notation, we propose that this pathway is not correct. We put a red cross, and that actually created and irritated people across. And I had to start fighting, scientifically fighting, that what was I proposed that we propose that is correct. So we propose that Lewis acid catalyzed reaction of aziridine and aziridine does proceed through an SN2 pathway, giving an enantiomer product, not always enantiomer product. So in this, our aim in this area at that time, that to develop new synthetic routes to aziridine, because those time even simple synthesis of aziridine, not many routes are there, even chiral aziridine. And to explore chemistry of these heterocycles, to study mechanism of ring opening processes, and then to apply this chemistry for synthesis of bioactive molecules, to control the racemizations of the enantiomer aziridine, so that we get enantiomer-enriched or enantiomer products. Because as a synthetic organic chemist, getting the product is not important. How to control the racemization, and finally to perform kinetic. So now I'm coming in the next couple of slides that we proposed in 2003 that Lewis acid catalyzed ring opening reactions of aziridines or aziridines do proceed through an SN2 pathway, not through the intermediates of a 1,3 or a 1,4 dipolar intermediate. However, in many cases, we did not get enantiomer products, starting from enantiomer aziridines or aziridines. So what is the problem? We found out that culprit is the racemization. So before nucleophilic attack, the starting aziridine or aziridine in presence of Lewis acid, it get racemized. That people could not sense. We had that idea. I'm coming in the coming slides. So our platform now, today's date, in after 19 years, we are still studying. So we showed it's SN2 reaction. Culprit is the racemization. So now platform is very much ready for dynamic kinetic resolution. So this is the idea we had that 15 years back. I will show you some of success. We got it in 2020. So now this is the your aziridine. Now see after 10 minutes, enantiomer aziridine in 10 minutes the room get totally racemized. So this after 1 minute, this is after 3 minutes. and this is we have shown from different minutes how it's racemized. So then, if you take again, question comes how to then control racemization. So we again visualize that if aziridine reacting with Lewis acid forming a deuteronic dipole, so there's some species the dipole-dipole interaction may stabilize this species and increase lifetime. So we again took the help of inorganic chemist around who is using quaternary ammonium salt, that is a dipole. So we use tetramethyl ammonium sulfate with our aziridine, and if you see that this aziridine it takes like at 0 degree it racemizes after 120 minutes, but if you add your quaternary ammonium salt, its racemization almost control up to 2 minutes. It is almost no racemization. So what is going on? So this is your aziridine, Lewis acid deuteronic species, and this plus minus is basically quaternary ammonium salt. So we found out that this is not the reaction pathway. This quaternary ammonium salt is controlling the racemization of the starting material. So what is happening in the racemization? Is dipole is forming? Yes, initially we thought maybe that is the thing happening. The dipole is forming. Then question if the dipole is forming, the reaction should go through the dipole. Now we don't believe the dipole is forming. The unreacted aziridine, it may again add as a nucleophile and cyclize back, and in that case you get the racemization of the aziridine. So again, use of polar solvents such as DMF, acetonitrile, THF, most of them coordinate with Lewis acid and hence diminish the activity. Use of polar additives such as tetrahydro ammonium salts, that actually played as a wonder. So this is the actually mechanism we've shown that this is your aziridine, this is your Lewis acid, and this is your quaternary ammonium salt. And I have not shown here today, I should have put it. We have done extensive computational studies where we have shown this species, like Lewis acid catalyzed, Lewis acid and this aziridine adduct, and your quaternary ammonium salt is hanging around. And at a particular time, there are the CN bond is stretched, and the SN2 reaction goes on. So because people will ask if there is SN2 reaction from here, this is the less substitute side, nucleophilic should attack here. Why nucleophile is attacking from the benzylic position? The answer is that the CN bond is stretched. It stretched such an amount that it can maintain a TPP structure. That is the geometry required for SN2 reaction, so that SN2 reaction is possible. So people will now ask, if that is the case, how to give convincing evidences? Then we asked ourselves, if that is if our proposal is correct, then nucleophilic Lewis, which in all three cases, the nucleophilic Lewis acid in presence of non-nucleophilic tetrahydro salt, like you take a nucleophilic Lewis acid, thus your quaternary salt is non-nucleophilic. In that case, then E should increase rather than using quaternary salt. Or case 2, non-nucleophilic Lewis acid. So Lewis acid is non-nucleophilic, but in presence of a nucleophilic quaternary salt, E should enhance. And third case, where both are non-nucleophilic, you take a non-nucleophilic Lewis acid and a non-nucleophilic tetra ammonium salt in the presence of a nucleophile. In this case, if there are enhancement of EE, then people will believe, yes, the proposal is correct. So for this first, so what we have taken, this 2-phenyl N-tesyl aziridine enhanced pure with zinc halide. So this is like your Lewis acid is nucleophilic, and quaternary ammonium salt like tetrahydro sulfate, tetrahydro triflate, perchlorate, and PF6. And if you see, without quaternary salt, E is around 40%. Now use tetrahydro salt with the chloride, zinc chloride, E is 82%, and with zinc bromide is 90%. From 40 to 90, 50% enhancement. Case 2, your tetrabutyl ammonium halide is a nucleophile. So benzyl trimethyl ammonium chloride, tetrabutyl ammonium bromide, tetrabutyl ammonium iodide, you see, is greater than 99:1. So fantastic. So our proposal is correct. And third case, and in the third case, we have I just I didn't mention. So when we got this result that there is a SN2 reaction, whatever available nucleophile, whether carbonyl, nitrile, olefin. We tried everything. The initial, I'm talking about 15 to 18 years old story. And in all the cases, we got enantiomer in this product. But obviously, those time we didn't have the idea how to control decimation. So there is enantiomer in these products, but the culprit was, that means the reduced enantiomeric excess was rationalized in all the cases by partial decimation of the starting acidity. So in this case, then we thought if the alcohol is a polar protein, then it should more it should support the SN1 mechanism. But in alcohol also we got up to 95% enantiomeric excess. So that was a great success for us. Then alcohol, in this case allyl alcohol, is 76%. Now you use quaternium solvent is 92%. In most of the cases, after using quaternium salt, 10 to 50% enantiomeric excess was observed. So now, this is the basically preamble of my talk. Now I'm telling. So we have shown the Lewis acid catalyzed reaction proceeds through SN2 pathway, either through 1,3 dipolar intermediate for a aziridine or a 1,4 dipolar intermediate from aziridine. So it's not. That means the reaction proceeds through SN2 pathway, not through the intermediacy of a dipolar intermediate. That is fine. So we have gone further. Then if our reaction, the nucleophile is tethered to electrophilic center. So that means ring opening. First is your ring opening, either NUE or a leaving group. So first, this case, nucleophile adds. So then your aziridine N minus, that is electrophilic center of the tethered nucleophile. So this can cyclize. And or there is a leaving group, this minus N minus, attack here, leaving group goes. This is called domino ring opening cyclization. That means Lewis acid catalyzed ring opening followed by cyclization in a domino fashion, or in short, domino ring opening cyclizations, or DROC or DROC. You can say this is Ghorai DROC. So, but there are other way. If that is not the case, our first step is a enantioselective or enantiospecific if 100% inversion is there. So that is the induction step. The first step is SN2 reaction opening followed by cyclization, because that time when we started in between 2010, that CH activation, CN cyclization. So that's why you say the first step opening followed by the second step cyclization is called ring opening cyclizations or ROC. So based on this DROC and ROC, we have done over the years many important scaffolds of contemporary interest. So this gamma lactam and your agipane, this agicane, this morpholin derivatives, agipane, quinoxaline. So this your indole, like this. So many inaminonitrile. So many things we have done that I'm not going in details all this. So this I'll show suddenly my first reaction, first paper. This is the first paper. As I said, we took aziridine, zinc halide as a Lewis acid, and dichloromethane. You can see that there is haloamines we got, and E is up to 78% when you started from enantiomer aziridine. Here also one story. Actually, when we are doing this reaction, Professor J.S. Jadhav, IICT Hyderabad, they have published some paper, this ring opening of aziridine with a indium chloride, bromide iodide in acetonide solvent. And in this case, they got all regio isomers, mixture regio isomers. So I told my students just to find out that in zinc case, what is your regio isomeric ratio? Oh my God, to our great pleasure and surprise, you take acetonidyl solvent, zinc bromide is a Lewis acid. Instead of haloamines, we got that SN2 ring opening cyclization or 3+2 cyclization type product, this imidazoline product. That was the very, very breakthrough in our reaction then. So we have found out what is the mechanism then. So we have found out if you take a haloamine, that is the intramolecular attack, it is up to 78%. And when you take this starting from 99% aziridine, you take nitrile, it is up to 40%. Most of the cases 10, 12%. So what happened? So once you, this going on, this N plus, it may undergo another SN2 reaction, so that there is a racemation of the this ring opening product, and we have further control that later on I will tell you. So then similarly, you take aziridine with a carbonyl compounds, you gave oxazolidine, and we got E up to 72%. Suddenly this result was before our discovery of using quaternary ammonium salt. Similarly, this your agitidine and carbonyl is the oxygenane. This is the first time we reported that oxygenane can be found. And in this case, the interesting part, the stereochemistry, we found out before our crystal structure. Then it was confirmed by crystal structure. So these are the old results. Now we return back to this, the first 2003 reactions with the oxazolidine, and one of the students recently graduated this 2021, Nobya Chauhan. She did a splendid job, and again we have provided convincing evidences that what we got 4% enantiomeric excess. Now we are getting 99% H2 excess. Single diastereomer, single enantiomer, just using quaternary ammonium salt. So there are this is the example, the mechanism, and obviously Lewis acid catalyzed and this quaternary cell coordinated aziridine undergoes ring opening by carbonyl, followed by cyclation. Suddenly this this phenyl and this bulky group of the R2 is to be the equal position, and you get that particular diastereomer. So again, another one, because this oxazolidine and imidazoline, it is very important biological point of view. So we came back to this problem again, and we found that instead of using this Lewis acid catalyzed reaction, you use aldehyde. You open the aziridine by amine, and followed by cyclation with the aldehyde in presence of PTS zinc magnesium sulfate. You get this imidazoline single diastereomer, single enantiomer. Similarly, if you take epoxide, you get single diastereomer of the oxazolidine. But I am not showing details of the mechanism because there are many things to say here. And then the first reactions we did, first reaction 2003 or 2002, end of 2002, that opening of aziridine with a amino acid ester enolate, but we are not successful. So in 2010 we came back after almost 7-8 years. Then we found out that if you take an active methylene group like ethyl acetoacetate, acetyl acetone, you put enolate and a Lewis acid which is activates the aziridine, open up followed by cyclation, then you get that several gamma lactams. And interestingly, if you take the phenyl aziridine, you get only single diastereomer, single enantiomer of the product. And if you take alkyl one, you get the mixture. And I'm not showing the mechanism of that very interesting mechanism. But in this was we patented because several bioactive neurotransmitter and drugs, Fenibat and all can be made. And we are waiting for the company to buy our project. Similarly, using the same chemistry, instead of ethyl acetoacetate, we took another nucleophile, that melonitrile. And in this case, that inaminonitrile, carbocyclic aminonitrile, it's a part of many natural products. Using the same melonitrile, you take potassium tertiary base and scandium triplet is the Lewis acid, which coordinates the aziridine, and this anion opens up aziridine, followed by cyclation to the CN, and then there is a tautomerization, and you get this inaminonitrile product. Very nice reaction. So, and after that, your 2010 Nobel Prize, that very hot CH activation, CN coupling, and all. So we thought, since our first step is the stereoselective and enanioselective step, so we can use the same chemistry, take this type of nitrile, and this nitrile minus aziridine opening, followed by CN coupling, that book or Hertz coupling, and you get this tetrahydroquinoline, and it is such a fantastic reaction. All you mix together, potassium tetrahydroxide, palladium, this, and the reflux in toluene, appropriate time, just filter it off. Single diastereomer, single enantiomer, and there is no other side product. Very, very nice. Next, we move for another scaffold, tetrahydroquinoxaline. So tetrahydroquinoxaline. So again, we have taken another nucleophile, bromoaniline. So bromoaniline, aniline opened up the aziridine, followed by again CN coupling with a palladium with the CN coupling, and you get this quinoxaline. Again, I have not shown here. This is enantiomeric pure quinoxaline. We can got it. Another important skeleton, this tetrahydro benzodiazepine. It's a very elite skeleton and important for very part of very important natural products. So in this case, again, we took bromobenzylamine. So again, this Lewis says a lithium perchlorate, ring opening followed by cyclization. In this case, interestingly, normal copper 1 and other palladium did not give us good result. So we thought, maybe why not copper powder? So question comes, copper powder is copper 0. How reaction proceeds? So we get many examples. And so this is also, it's a hard job for me to write the mechanism and convince the reviewers. So copper powder, in that it's like our the normal solvent. So they are dissolved oxygen. It oxidizes copper powder to copper 1, or there is little bit of contamination of copper oxide in copper powder, and that gives up reaction, and copper oxide that disproportionate to give copper and copper oxide CO. So at the end of the reaction, you get black copper oxide. That's why you need super stoichiometric amount of copper powder. This is also a very fantastic reaction, environmental friendly. You do the reaction, just put copper powder, heat it, and you get the product. So another interesting skeleton, indoline, and especially 3-substituted indoline making is very heterosubstituted indoline is very difficult. But we synthetically manipulate our starting material. We use orthochlorobromo-phenyl aziridine and with a copper trifluridine and some heteronucleophile, thiol or amine. It ring open and followed by CN coupling, you get this indoline. Very nice reaction. And I'm not going to the biological activities of all this compound. It's showing all are biologically active. And this as the alternative routes for your indole synthesis. Indole is a very important molecule, part of several natural products, indole alkaloids. So, and to make 2-alkyl indole, the normal method is that indole you deprotonate at 2 position with bitter lithium and all, and then do alkylate. But problem is that if your skeleton is having halogen and all, the reaction fails. So what we did, we have used this method of indoline and used thiophenol catalytic amount. So you get this the compound with a S pH, and in the copper mediated your oxidative cleavage gives this product your indole. So that means, so if you take a aziridine cis trans mixture, doesn't matter. So you can have this 2-substituted indole. So you can have your so you can have various halochlorine, chloride, fluoride, this halogen atom. Even you can put alkyl cyanoester at 2 position. Very nice reaction. And I'm not showing the mechanism. And if somebody is interested, so here is S. So S will again donate electron to the copper, and then it will be next is your copper mediated reaction, and then this radical cation, and this there is elimination. S pH goes, thiophenol as a comes out, so this catalytic thiophenol is good enough, and you get that indole. And obviously based on your mixture of systems, so you need to prepare purify the systems, the mixture you add, because finally you get the aromatic product. So we get this indole. It's a alternate to known indole synthesis method. We have patented this also. So we have shown, I have shown a couple of slides back, this synthesis of benzodiazepine you take that orthobromobenzylamine, but there is no handle. So further functionalization is not possible. We thought maybe, okay, you take this, you take this alcohol, so acrylates with the ortho positions phenol or amine, and then this amine will ring open followed by Michael addition. But unfortunately, that so ring opening followed by Michaelisons did not go. So we have to use this palladium-mediated cyclation. It's a fantastic reaction. So you can have so tetrahydro benzodiazepines and tetrahydro benzoxodiazepines, both like an oxygen and nitrogen substituents. Both this is the diazepine. And what is the mechanism? So this is your ring opening followed by yes, palladium is coordinates and activates the double bond, and then its cyclations goes on. And if you see from here, this palladium is from the top phase. So this and this is from the bottom phase. So that's why you get this one as a up phase. So that means you get the cis. So this also gives us a lot of trouble to find out the geometry of this one. So this paper we have published as a feature article. I mean, featured in the cover page of 2007. That's the first time 2 papers in a single issue made the cover page. I'll show you the last. The 2017 first issue, first cover page is ours. So then another important skeleton is called hexahydropyrrolindole. So I'm not showing the molecules. There are plenty natural products or bioactive molecules contain this skeleton. And interestingly, I'll tell you, we published in 2017 as a featured article and a cover page. In the same year and 1 year back, people published in Josie and Jax. And my student was sitting on this because he got diastole ratio 3:1, 2-3 years. One day I told him, "Arey, just look into it." Then I see the people have published this paper, Jax and others, the ratio DR is 3:1. So one fine morning I told him, you do the reaction, in the same pot you add sodium naphthalene. It's our fortune, and the detosylation, and that lead to the separation of the diastomers. So we got clean 2 diastomers separated, and this is the basically history in this field, you can say, because so ring opening by aziridine from the 3 positions of the 3-alkyl indole and followed by cyclation and give this product as a single enantiomer and very high a single enantiomer, single diastomer, and it's a very high yield. Now another important and 2 important skeletons are synthesis of 1,2,4 oxadiazepines and 1,4,2 dioxazepine via this DROC of activated aziridines with epoxide and nitron. So we take aziridine and nitron, and this reaction is important because we have done the reactions in water, just water. So in water, you take aziridine, you get oxadiazine or 1,4,2 dioxazinanes. So this, if you take epoxide, dioxazine and oxadiazinanes. So these 2 compounds you get, and you get single diastomer, single enantiomer. And one interesting part is you take the mixture of cis trans and you get only single diastomer. So this is the first time we have shown aziridine there's a dynamic kinetic epimerization, because your first step is your SN2 reaction, I said. So during the reaction, I said that there's a racemization, and so in this case, it's a control of racemization by quaternary salt and racemization to give the most stable trans diastomer. Cis to trans is most stable, and you get single diastomer. There's a trans of the product. Fantastic reaction. This is called dynamic kinetic epimerization. And what is the mechanism? So if you have your nitrogen, so first is your oxygen attacks from here, and this then nitrogen attacks from the psi phase, and you get this product as a single diastomer in the form of the. So and it is basically 1,4 cis, and for the aziridine and on the epoxide because of it attacks from the rephase, you get this dioxazine as a single diastomer. Now another important skeleton is your beta carbolin, tetrahydro beta carbolin. So what we thought, so these three positions of the indole is nucleophilic, and it opens up the aziridine. So we took activated vinyl indole and activated aziridine with presence of lithium perchloride as a Lewis acid. So this aziridine undergoes ring opening from the three positions of the indole, and followed by cyclations from the end as a Michael fashion. You get this. There is a diastolic mixture some cases, and some cases you get single diasteromer. So this is also very, very important skeleton we published a couple of years back. So these are the mechanism, and these are the more favored. That's why you get the major one, and this one is because of the steric congestion. So this is the less favored, and we get this on cis as the only product, means major product, and trans is the minor product. So same beta carbolin, tetrahydro beta carbolin, we made another method because once we start, we are, because there is a, but again also we thought we get better diastole selectivity, but we didn't get here also. What we did, again, ring opening of aziridine from the indole from three position, followed by Spiegler reaction. So that gives the your tetrahydro beta carbolins in a very good, moderate to good yields, and with a you can say moderate diastole selectivity. So these are the mechanism: ring opening followed by your carbonyl, and this is your carbonyl, and this is a 6 endotic cyclation, and from the 6 endotic cyclation, psi attack favored, and you get the major diasteromer. So this basically amine and this aldehyde in the PTSA from the imine. Iminium, and then you get this cyclations from two positions, and followed by aromatization, you get this product, major product. Another interesting, imidazoindole and so these are two regioisomeric imidazoindole. Two regios, because one is phenyl, one is alkyl, R1, R2. You see that here, this R1 and R2. If you see N, so this is N, this is R1 here, R2 here. So it's a very interesting reaction. You take this 2-bromoindole and 2-bromoindole. So 2-bromoindole, you take recombination. So this is path A. So path B, you put a base. Once you put a base, this is minus. It's a very bulky nucleophile. So if you have phenyl, and so it's a less substitute site, it attacks. So like R2 is a less subsite. So it attacks from here, then followed by cyclation. And in this case, you have your dibromovinyl aniline, and in this case, your aniline N is it's a lesser bulkier, opened from the phenyl side, and once you then it cyclizes in a two domino fashions, one after NH, and followed by, so this cyclized. So this cyclized here, and then 1-bromo, and again this cyclized. So you can have 1, 2, 3, 4, 5 here, and again 1, 2, 3, 4, 5. So 5, 5. So that means starting from the same starting aziridine, using two different kind of indoles, two different conditions, you can have two regioisomeric imidazoindole. This is the mechanism for the students' benefit. So this is your Lewis acid and your ligand and copper on this complex, and then Lewis acid activates aziridine, opened up by your aniline, and this your copper, your CN coupling, and again in the domino fashion you get this. Another case, you NH put sodium hydride, it's an N minus, it opened up from the less substrate, this side, because the bulky nucleophile, it's a steric hindrance will dictate attack from the less substrate side, and then CN cyclation. Now, a couple of slides back, you have seen that how to make tetrahydroquinoxaline. So you take that orthobromo aniline, and your cyclization, ring opening followed by cyclization. But the same reaction, we continued further, that tetrahydro N-tosyl quinoxylene in the ring opening followed by your copper 1 proline sodium hydride, and heat and DMF at 125 degree, you get this quinoxylene. And obviously quinoxylene is a very important skeleton biologically active molecule, and we have actually patented this method, and we have made this your trypsostin AG. This is a PDGF receptor tyrosine kinase inhibitor, and its cost is 5 mg is 13,000, and ours is maybe 5 gram will be less than 10,000 rupees. So what's happening here? So first one is your ring opening of aziridine, followed by oxidative addition and your cyclization. You get this your reductive elimination, you get quinoxylene, then sodium hydride, and you sodium hydride you get detosylation. So detosylations, aromatization, and again single electron transfer from this aniline, this amine radical cation, and followed by aromatization, and you get this fantastic reaction. So ring opening followed by cyclization, followed by detosylation and aromatization, you get quinoxylene, and that obviously, and every skeleton we targeted that is having a biological important molecule that we targeted, and try to continue that method. Another important skeleton is your benzoxazine. So this is benzoxazine. You take the bromophenol, very easy, lithium perchlorate, ring opening followed by your CN coupling. So no problem. You get single diastereomer, single enantiomer, and after detosylation, you get this is NH free. And interestingly, once you start from enantiomer compounds, we are struggling to get enantiomer compounds. And then we found out, since the phenol is a nucleophile, if you put base, it's a phenoxide, better nucleophile, and it opened off your aziridine, and we enantio specific way we got the benzoxazine in enantio pure form. Beautiful reaction. And this method again we tried because many of you know this molecule. Levofloxacin is antibiotic. Pneumonia, acute bacterial sinusitis, those who have sinus, urinary tract infection, acute nephritis, not nephritis. So this molecule, we have a synthesis of this, formal synthesis. So from starting from this difluorophenol, we got this, and this was used as a nucleophile to open the methyl aziridine. We got this product. Then we have a detosylation, and from which there is a reference known to make. We have not done this because by this time student left. So this is a very interesting chemist we have shown. Now another interesting thing, your azepinoindole. So azepinoindole derivative or diazepinoindole derivatives. How to make from aziridine? This is the indole, again synthetically manipulated to use 2-bromophenyl that's indole, ring opening again from 3 position, followed by CN coupling, and this beautiful skeleton we got. And this is this is very important biologically. Some Surag disease, and we actually we have done the biological study with Eli Lilly, and they say there is 100% inhibition. Finally, they have stopped this MOU with us. I don't know what's happening there. So these are the examples, and you get very enantio NDs. That means some cases enantio pure product, starting from not enantio pure, almost 98% enantio reaccess, very high EE, starting from enantio pure aziridine. We got this type of molecule, and these are the mechanism as I said, from 3 positions of indole, ring open, and followed by then rearomatization and your oxidative addition, this normal CN coupling, oxidative addition by copper coordination, and reactive elimination, you give the product. And as I said, The other benzodiazepine, not diazepine, diazepinoindole. So diazepinoindole, to make diazepinoindole, you take indole and base, so that the nucleophile is a minus, and that opened up from the your less substrate side here, and so less substrate from here and like here. So that's why the CH2, and followed by cyclization, you get the you get this diazepinoindole derivatives. Now very interesting. All are interested today's date now. CH coupling, CH activation. We also thought if first step is a SN2 reaction, why not our method give a CH activation? So we designed this N-pyridyl sulfonyl aziridine, and then again pyridyl sulfonyl aziridine opened by nucleophile like alcohol. We have shown the various kind of alcohol, and followed by the same copper acetate. It was activated this phenyl ortho hydrogen and give this CH activation, and you get this 3 substituted indole fantastic reactions we have published in a couple of years back. Oh, sorry, I have not. Oh, this is a mechanism. So first is your SN2 reaction, alcohol with the Lewis acid, you get this product, and now this copper acetate and this this pyridyl sulfonyl, the pyridyl group, pyridyl copper. So this gives this copper this phenyl group ortho position activate CH activation. So CH activation and followed by your cyclizations, you get this product. So this is a first example we have shown in aziridine CH activations to get enantiomer pure products. Another interesting skeleton is tetrahydropyrimidine. All you know, tetrahydropyrimidine is a part of not only your DNA bases. There are many important molecules. Like these are the I have shown. I'm not going details about the biological activities. All these molecules, like boron tail and those. So how to make this skeleton? So we visualized that if you take tosyl methyl isocyanate. So this is a earth is a tosyl. Tosyl is methyl isocyanate, triple bond N, triple bond C. So if you take a potassium tertiary is a base, this anion, and it will open up the aziridine, Lewis acid activated aziridine from the phenyl, and followed by this is a tautomization, and followed by six indodic cyclizations, you get this tetrahydropyrimidine skeleton. And I have not shown here. In most of the cases, we got enantio pure compounds, and enantio pure compounds. In this also people use in the literature. There is a lot. I'm not going to the controversy. I just leave it. So now this your another important skeleton here. Spiropiperidinoindolenine. This also various natural products having this skeleton. And we thought if your ring opening of aziridine by indole from 3% is very facile, so we utilize that your pi-LL complex of propagyl carbonate. So ring opening by your ring opening by indole, followed by cyclase with propagyl carbonate, and give this type of spiroindolenine via ring opening and cyclization. So these are the various examples, and we got up to in a 99% access. This also patented because of biological activity of the molecule. What's happening here? So the first is your ring opening from 3 position, you get this one, so rearomatization. Now you have a propagyl carbonate, palladium 0 is some like a pi-LL type of complex, then followed by this type of alene type of intermediate. And then decarboxylative oxidative addition with this, we get this oxidative addition, and followed by proton migration. So proton migration is from this NH minus this one, the proton migration, and followed by your cyclizations from here, from the 3 position, you get this, and reductive cyclization, and followed by reductive elimination, you get this product, your spiropiperidinoindolenine. Fantastic reaction. So using the same line, we thought we have shown tetrahydroquinoxylene. If this is the case, that your aziridine opens up by indole C nucleophile followed by your propargyl carbonate. So we can make piperigine derivatives with a strategy where we use, instead of indole, aniline as the nucleophile. So aniline will open up the adenine ring, and then followed by propargyl carbonate, and you should get this piperigine derivatives. Interesting, we got good to high yield, and this is the mechanism. So first is your ring opening by your aniline, and that's your propargyl carbonate decarboxylation. From this, your alene type of palladium intermediate, palladium species, which undergoes oxidative addition. Once you have oxidative addition, you get this species. Again, the same mechanism, followed by your proton transfer and cyclations, followed by reductive elimination. We got this exocyclic double bond. I mean, piperigine is exocyclic double bond. Very, very nice reaction. Now, very interesting. There is a so we have this reaction we have shown in the last slides I had shown. There is a report by my friend Purnamurthy from IIT Guwahati. They used propargyl aniline. We took aniline and propargyl carbonate. They took propargyl aniline, and the copper and this system. What they got again this your piperigine derivatives, and this isomerase to give this endocyclic like enamine type of thing. We thought, well, we have not taken any in a Lewis acid. We took neat conditions, we ring open followed by palladium cyclation. So what will be our reaction, fate-over reaction in the presence of Lewis acid? And to our great pleasure, great surprise, we got a totally different product, not the piperigine exocyclic double bond or endocyclic double bond. We got tetrahydro, tetrahydro piperigine, we didn't get. We got hexahydroimidazoquinoline. So hexahydroimidazoquinoline. Bhaya, it's a fantastic reaction. I don't know why we lost very big paper, but anyway, we're happy with the organic later. That also very nice paper. Unfortunately, the big paper, if you 1:1, I know you have to compromise. So here, SN2 reaction followed by hydroarylation, followed by hydroamination in the same cascade fashion. So these are the examples: single diastereomer, single enantiomer, and so these are the this case we got 99%, in other cases we got 96, 97%. What is the mechanism? So first, your propargyl aniline. So Lewis acid activated or coordinated aziridine undergoes ring opening by propargyl aniline. Then your minus H plus and your, this is the species form, deprotonation, protonation. Then this amine, this undergoes hydroarylation. See here, hydroarylation. You get hydroarylations here, hydroarylation, and then, so this is actually what? 1, 2, 3, 4, 5, 6. So 6, yes, 6 endodig diagonal, 6 endodig cyclations, basically hydroarylation, followed by isomerization of the double bond, and again addition of this amine, hydroamination. So SN2 type ring opening, followed by protonation, deprotonation, followed by hydroarylation in a 6 endodig cyclation, followed by hydroamination. And interesting, people might ask, why this your isomerization? Because in this case here, so this is zinc. So this is actually if you have so there is a question that it might from here, then it might nitrogen and oh no, fine. So this is your, just a minute. Yeah. Then and then we have your Then you have cyclation. Fine, I'm sorry. So this is fine. Yes, this is 6 indole. So then I'll just talk about some of the agitating little bit. Because there are many things I skipped because of time constant. Now this agitating also, there are not many reports are there because there's a competitive allyl information. And we have shown many agitating chemistry. I have not included much of here. Only one molecule we have used, this tolterodine. So this is the molecule. This is actually it's a drug used for your expansion of urinary bladder. So the old people, their urinary bladder sinks and then always feel urinating. So this drug is used. So we thought, let us try this method whether we can make this drug. So this nucleophilic opening of agitating with a this is carbonucleophile like electron-rich aromatics, and then like this trimethoxybenzene or other thing, and followed by synthetic manipulations. I'm showing that. So this is your paramethyl anisole or paramethoxytoluene with a in place of ytterbium triplet. This undergoes ring opening, followed by your alkylations of this NH isopropyl, and then this 4 again another isopropyl, and then your removal of the methoxy group. You get this. This is a tolterodine, and these are very simple steps. And we have patented this molecule also, and we are doing now enhanced selective synthesis of this molecule. And another one is your if you take this indole and agitidine ring opening from 3 position followed by CN coupling, then you can have tetrahydroazepinoindole. This is also very important skeleton. Is a 765, and we have got very good yields. And again, purpose is that we have synthetically manipulated this one to the vasopressin B2 receptor antagonist. From this method, detosylations and further manipulations, you can get this. So now people may think that our audience that Ghorai is not maybe publishing last 2 years. What happened to his group? Actually, because of pandemic, my students are not there. We have results, but I'll tell you the many important things are there apart from old results. So this is one actually conjugated organic polymer. If you use that, used as actually donor acceptor catalyst, and which triggers ring opening followed by cyclation and give this type of imidazoline derivatives. This is all unpublished results, and because of this reason, I'm not because nothing is published, and we are working in some metal chemistry as well. So we synthesize some conjugated organic polymer which does this job as an electron donor acceptor, and it forms this radical cation. And so these are the before your polymer. After this is the color, and then this is another one. So this is actually another reagent. Instead of Lewis acid catalyzed reactions, we have done some of the reactions in terms of some of the catalysts, which is oxidant. It's a wonder. So with a minutes reaction does. You see this alcohol where it's at 20 hours, 23 hours. It's at 5 minutes, 10 minutes, and so transition metal free reaction, high yield, high E, broad substrate scope, optimum reaction condition, less reaction time. And these are the again the same reaction that tolterodine I have shown that you have done with a Lewis acid, and in this case we are trying with a this electron-rich olefin, and I'm not disclosing that. Now my dream project, as I said, we have so far we have shown the Lewis acid catalyzed ring opening reactions of azidine does proceed through an SN2 reaction, not through the interface of a dipolar intermediate. And we have controlled the racemation, but now we have shown SN2 reaction. We have shown there is a racemation possible. So now we want dynamic kinetic resolution, starting from racemic agitidine or agitidine here, agitidine or agitidine, and you take a chiral entity, means chiral Lewis acid or chiral cotton ammonium salt. There is a ring opening of reaction. Where one of the agitidine will be undergoes ring opening reaction, other will be converted, racemized to the other one, and you get this type of only one major product. So some examples. So these are the result we got 10 years back. One of the MSc project student got, then our PhD student. But whatever catalyst we have, we didn't get any good success. We got up to 12% EE and 20% agility back. As a, so now with a modified catalyst, I have some very active group. One of postdoc, Dr. Prashant Ray, and with his team, Divya Sestha and Amit Sharma, they are doing their best. Now we could show that dynamic kinetic resolution is possible with our substrate up to 87% EE and followed by cycles to the same product. Similarly, another substrate, we got up to 82% EE. Obvious reason, I am not showing the conditions because it's not published yet. And these are the KR. We could show the kinetic resolution also. And we have seen that 99% your other enantiomer of the agility is back, recovered, and this molecule get up to 98%. So to conclude, we have demonstrated that Lewis acid catalyzed opening reactions of active agilins to proceed through an SN2 pathway to afford chiral products, contrary to the earlier literature reports involving the intermediacy of a 1,3,1 dipoles, which would generate products in racemic forms. Synthesized substituted chiral agglutins from naturally occurring amino acids. Ring opening transcription involving these heterocycles provide excellent routes to important non-receiving nitrogen-containing targets. Stereoselect ring opening SN2 has been extended to D-cyclopropanes that I am not shown today here because of time constraint. The new synthetic route to chiral gamma-lactams, dihydropyrols, carbocyclic enamino-nitriles, tetrahydropyrimidines, etc. You have seen many scaffolds we have done. Dynamic kinetic resolution of agilitins provide the way of synthesis of chiral nitrogen-containing products from the racemic substrate. Finally, this is that I told about your cover page. There are two. One is your DROC, one is ROC. This is those the Bengali, they will know. I wrote in the GOC the Tubri. So this is like your Juribati, and this Lewis acid does this job, and then it's like bloom, like Ukraine. What is going on? You can have a plenty of molecules with a glittering lights, and these are the. Without that, my I'll not do it justice. I am just a storyteller. This is the real player who played over the years. Now this is the player who is working now, present members. I am just, they made the story. I just told you the story in a convincing manner. These are the money I owe to them, DST, CSIR, and finally, Venkat knows that IIT Kanpur is a dancing peacock, and this is our southern lab. Our lab is located here, and we are most welcome to visit IIT Kanpur. Thank you very much for your kind attention. I'm sorry I took a couple of minutes more because I came late.
No problem, sir.
Thank you very much.
Thank you so much, sir, for your wonderful lecture. So now the lecture is open for questions.
Yeah, maybe I have 1-2 questions to share.
Yes, sure.
Yeah, it was a nice lecture from you, sir, to listen to you, and you have demonstrated your work very nicely, I would say. I think I have connections with you, like because you did your postdoc in Würzburg, but I was also there in Würzburg doing my postdoc.
Oh, great, great.
Yeah, with Holger Braunschweig, I just did my postdoc. Yeah. So I have questions like you have used sodium naphthalate.
Yes.
In one of your reactions, I
Yes.
think in slide number 33 somewhere. So that is like to give some electron push from somewhere, or it's like a reducing agent?
We say N-tosyl, no. It's just because detosylation, nothing else.
Okay, for detosylation purpose, you added
Yes,
sodium
because
naphthalate.
students are struggling. We use that magnesium, methanol, mercury, nothing worked. I told just dump in that after reactions, you put it there. Same good reaction mixture, you did it. So it's just for detosylation.
Okay. And you were mentioning in your recent studies about your some polymer like COP.
Yes.
So it's like a kind of a organic polymers, or
Yes,
you
organic
want to reveal that? What is that, or next?
Yes, organic polymer. So it's a very, very known. I'm not shown because it's not done, because we have done some on that. We have done your water splitting. We have published one GMC paper last year. And so from that, we got the idea, instead of material chemistry, whether we can use this for organisms. Whereas, I'm not disclosing, say, 1 mole percent, the polymer you add this reaction, what is struggling for ED or monitoring, this just goes. Because this is having a donor acceptor, both things are there in the polymer. But sorry, I'll not disclose the polymer today.
Yeah, sure, no issue. Okay. And okay, that's all from my side. Yeah, Venkat. Yeah, you can carry forward.
Yeah.
Thank you, sir.
I have a few questions, sir. In slide number
Yes.
10,
Yes. Yes.
yes, sir. So here you have shown the salvation of the intermediate by the
No, it's not a solvation.
tetraalkyl.
No, this is not solvation. I am to just show that it's a dipole. So quaternary ammonium salt N plus X minus. So this inside is your deuterium N plus Lewis acid minus. It's like we have shown in our theory that your almost it's like it's hanging around plus minus plus minus plus minus plus. That's why I maybe could not portray properly. It's not solvation. It's just it's a dipole interaction.
Yeah, yes, sir. And sir, in slide number 21, I have another doubt regarding the mechanism and
Yes.
yes. So here, sir, depending upon the size of R1, R2, suppose if R1 is alkyl and R2 is aryl, and they are going to occupy either axial or equatorial.
You get mixture of diastereomer because mostly you have used all aldehydes. No, one is H, other is phenyl or alkyl. So this is easy for us. But if you take a mixture, that you make a mixture of diastereomer.
Oh, okay. So whenever there is R1, R2 different groups, then you get diastereomer mixtures. Yes, sir. So, is there any other studies? Yes.
Even
Yes,
H and alkyl also, some and aryl, we get some cases mixture of diastereomer.
Okay, sir. Sir, in all of the studies, these aryl aciridines are used. So what happens, sir, if the aryl group is replaced with alkyl aciridines, for example, methyl?
We have done because if it's alkyl, we believe, and we have that paper is coming now. So then also again controversy, they took methyl. They took methyl aziridine and this oxazolidine and on Chemcom paper, and there's a lot of controversy. He says again dipole. I said it's like your hyperconjugation. The incipient carbocation delta plus is stabilized by hyperconjugation. And if you keep on changing the steric bulk, methyl to isopropyl to tertiary, then obviously it will open from the less substitute side. That also you have shown. So you take methyl to methyl side, isopropyl mixture, tertiary from other side. But you have methyl with our condition E99%.
So again, it is SN2 reaction, not SN1 reaction.
Now I don't think that dipole is forming at all. I am fighting with people who don't know dipole.
Yes, sir. Yeah, that is very nice. So if then maybe it can be done for all the substituted aciridines.
Oh, yes. So even alkyl, phenyl, styryl, alkynyl, silyl methyl, all the cases SN2 reaction. Professor Sari is not no more. Sari used to tell me no. I used to fight. Professor Junjappa and me we used to discuss many times because this which gen has said that's one. I said whatever they said. I cannot say that they have told wrong, but I have provided convincing evidences in support of my mechanistic proposal. This much I can say. So yes, I have 5 all big guy, Brian Stoll, Paul Oender. I'm telling India, though I'll not tell the name. So I had a fight. So no problem. God knows maybe.
Yes, sir. So here you used aciridine or sometimes epoxides. So what about styrene? If we have a sulfur, so you plan to do any?
No. Actually, we have done aziridine. Then we have closely see that we have see that similar skeleton is the biologically active molecule. So we said, then why not? Then you have seen that it's going, and the same chemistry is going. So that's now you see that epoxide, aziridine, cyclopropane, even cyclopropane are fighting with me. They also say all Michael Kane and all, they said the dipole. I said there is no dipole. It's cyclopropane also SN2 reaction, and the DROC actually given in the cyclopropane context. And this is my terminal. You just Google it. Only my name will come.
Yes,
So the
sir.
DRS is given by myself. It should work. It should work.
Yes,
We
sir.
have not tried. It should work.
Sir, in slide number 40, I have another question. Slide
Yes.
number 40.
Yes.
Sir, in case if you block the third position of the ring, and then will the reaction go at second position? Suppose if you have 3-methyl indole, and will the reaction go at 2 position of the indole?
So if there are three position that we have shown, if 3 position is there, then
Yes, sir.
it will immediately cyclize. That give that tetrahydropyrrolindole.
Yeah, no, sir. If you take the
Yes.
3-methyl indole,
Yeah, 3-methyl indole. If you
yes,
take that,
then
first
will the second position of the indole react with the acidity?
no, immediately that N, no, that we published that cover page, no. So that N minus will cyclize here. This is the iminium cation, it cyclize here. So you get the pyrrolindole.
Yeah. Yes, sir. Yeah, that's all, sir. So
Okay.
thank you so much, sir, for wonderful chemistry, starting with simple acidine, but all the different kinds of heterocycles you have synthesized and published in very good journals.
Okay. Thank you very much.
So any other
See you
questions
someday.
from anybody? Any questions, students?
Actually, for students' sake, I just give the background of the work, how they will be motivated, how I was no interest for doing aziridine, but I was serendipity. Now it's becoming my bread and butter, one part.
Yes, sir.
Okay, thank you very much.
Yeah, yes, sir. Then maybe.
Okay. Thank you, sir. Thank you for your time.